Hi, you should remember my having mentioned Carnivora a few times. We revisit them again today. Fossil taxa are inherently at a disadvantage in resolving phylogenetic relationships relative to living forms, as soft anatomy, DNA, physiology, and most life history attributes are not readily available for the vast majority of these taxa. Nevertheless, fossil data possess several key advantages in phylogenetic analyses, including the ability to break up long branches in phylogenies, where the divergence between modern-day clades occurring deep in geological time. Fossils preserve morphologies that can become obscured along these long branches, and also provide temporal context for the evolution of living clades that may be crucial for accurately reconstructing ancestral conditions and partitioning synapomorphic versus homoplasious resemblances among modern-day taxa. Some workers feel that molecular data are inherently superior for reconstructing phylogeny than morphological characters, and as a consequence, phylogenies for many clades, particularly those that are not well represented in the fossil record, often are based solely on molecular sequence data. In contrast, those studies seeking to integrate fossil taxa into an evolutionary context together with living species de facto have tended to emphasize morphological data. The advantages of nucleotide sequence data for studying phylogeny have been shown to include a number of potential characters available for comparison, rate independence between molecular and morphological evolution, and utility of molecular data for modeling patterns of nucleotide substitution. Potential pitfalls have been revealed and include difficulties of inferring positional homology, incongruence between organismal and gene genealogies, and low likelihood of recovering the correct phylogeny given certain patterns in the timing of speciation events. Total evidence phylogenetic analyses incorporating all available data into a single data set are becoming more common in analyses of extant taxa, as well as analyses incorporating fossil and extant taxa. This approach arguably is preferable on methodological grounds, as it incorporates all potentially phylogenetically significant data within a single analysis. Indeed, empirical studies have demonstrated that data combination can be superior to congruence-based approaches. In this lecture, I provide a summary of recent phylogenetic analyses based on primary character data for the Carnivora and their closest extinct relatives, basal members of the more inclusive clade Carnivora morpha, with brief consideration of their nearest sister clades among the Eutheria, while preference is given to synthetic total evidence analysis when available. We review the spectrum of most inclusive analyses currently available for a broad array of higher-level clades within the Carnivora morpha. The intent of this lecture is to provide exemplars of the types of interesting evolutionary studies that can be developed within a robust phylogenetic context, and I present discussions of some recently published analyses and works in progress by the authors. Studies that can incorporate fossil taxa permit direct assessment and evaluation of the additional information that can be provided by such fossils, including constraints on divergent ages, morphological attributes of basal members of clades, and enhanced understanding of ancestral reconstructions for these groups, biogeography through time, and so on. Various aspects of the phylogeny of crown clade Carnivora and the more inclusive Carnivora morpha have been well resolved by morphological data for some time. Some higher level interrelationships have remained controversial or poorly resolved. The increased prominence of molecular phylogenies as well as total evidence analyses has led to resolution of many areas of ambiguity or conflict. In addition, there has been long-standing uncertainty about the placement of key fossil taxa, such as the closest early Cenozoic relatives, traditionally the Myocoidae or basal Carnivora morpha, and the extinct Creodonta, some of which is beginning to be resolved through more comprehensive sampling of taxa and characters and broader integrative analyses. Flynn and Wesley Hunt, 2005, provided the most recent extensive discussion of these phylogenetic issues and results. Myocoidae is a paraphyletic superfamily that had been traditionally divided into two families of carnivores, Myacidae and Viverrividae. Myocoids were primitive carnivores that lived during the Paleocene and Eocene epochs, about 66 to 33 million years ago. Today, Myacidae is recognized as a paraphyletic array of stem taxa that probably resulted in some Myacid genera ending up just outside the order Carnivora, the crown group within the Carnivora morpha. Carnivora morpha consists of both Myocoidae and Carnivora, but excludes the order Creodonta that existed alongside Carnivora morpha. Myocoids are regarded as basal Carnivora morphs. The Myacids are a paraphyletic group containing all myocoids that are not viverrivids. Morphological analyses by Weiss and Flynn 1993 and Wesley Hunt and Flynn 2005 provide support for the long-standing notion, see e.g. Matthew 1909, that Creodonta are the nearest relatives of Carnivora morpha. Molecular results generally indicate that Pholidota are the nearest living relatives of Carnivora, although there is disagreement among molecular studies, variability in taxon sampling and topologies among various molecular studies, analytical algorithm applied, and only weak morphological support for this hypothesis. Virtually all recent cladistic higher-level phylogenetic studies provide strong measures of nodal support for monophyly of the Carnivora morpha, and numerous monophyletic subclades. Examples include monophyly of the crown-clade Carnivora and the division between its two major subclades, Caniformia and Feliformia. The Caniformia subclades Arctoidae, Pinnipedomorpha and Pinnipedia, and Musteloidae. The Feliform subclades Phylogeny and Herpestoidae, and monophyly of all traditional modern families, except Viverridae and Mustelidae. Many lower-level subclades of these groups also are well resolved, but others remain the focus of intensive study. Monophyly of the Pinnipedi, with the Pinnipedia initially of uncertain relationships within the Arctoidae, but now definitely shown in several studies to be more closely related to the Musteloidae than to Ursidae. In addition, the Odobenidae are consistently resolved as more closely related to Otaridae than to Phocidae. Skunks and stink badgers, Mephitidae, are not included within the Musteloidae, sensu stricto, contrary to their traditional taxonomic placement, but rather form a distinct clade unto themselves. Nandina is the sister group to all other living feliforms. Linsangs also are not vivarids, but instead appear to form a clade, Prionodontidae, that is the sister taxon to the Felidae. Madagascar's feliform carnivorans, species of which have been variably included within Felidae, Herpestidae, and Viverridae, instead comprise a monophyletic clade, Eupleridae, that is the sister clade to the Herpestidae, bearing significantly on interpretations of their biogeography. Within Herpestoidae, Hyenidae is the nearest relative to the clade, Herpestidae plus Eupleridae, although the interrelationships among Herpestoidae, Felidae plus Prionodontidae and Viverridae, sensu stricto, remain controversial and are best represented as an unresolved polytomy at this time. The phylogenetic position of the giant panda, Ailuropoda, which has been considered problematic taxonomically, although morphological evidence has long supported its position as an ursid, is strongly supported as basal to all other living ursids in recent morphological, molecular and total evidence analyses. The red panda, Ailurus, is placed within a family, Ailuroidae, that is monotypic for living taxa, but which has fossil representatives, and this clade remains in an unresolved polytomy between Ailuroidae, Mephitidae and Musteloidae. A polytomy is a section of a phylogeny in which the relationships cannot be fully resolved to dichotomies, thus giving many temporally based branches. Recent phylogenetic work among extinct taxa has emphasized molecular data, although the number of loci and total number of base pairs and the proportion of living species sampled vary substantially across studies. Studies of relationships among living carnivora alone hinders development of the most meaningful and comprehensive view of their evolutionary history, as it ignores key character states and transformations, temporal and biogeographic data associated with the rich diversity of early carnivoromorphan fossil taxa, as patterns of morphological transformation during the initial diversification of Carnivoromorpha can only be accurately determined through enhanced understanding of the relationships of basal taxa, specifically early Cenozoic members of this group. The Nimravidae, false saber-tooths, are an archaic group of saber-toothed carnivoromorphans, initially considered to be close relatives of Felidae, but now of uncertain placement as basal feliforms, basal caniforms, or even outside the carnivoran crown clade. In addition, it is unclear whether the hypercarnivorous barbophelines are members of the Nimravidae or instead represent another independent evolution of a saber-toothed carnivoromorphan clade. The Amphicyonidae are an extinct lineage often referred to as bear dogs because of anatomical resemblances to members of both groups. They are of uncertain phylogenetic position. In recent studies, the Riveravidae is always found to be monophyletic and represents the nearest sister group to the remainder of Carnivoromorpha. These are the earliest Carnivoromorphans in the fossil record, first occurring in the early Paleocene of North America and ranging to the late Eocene across Europe and North America, with the last known specimens also found in North America. All species appear to have been highly carnivorous, with the smaller taxa perhaps more specialized for insectivory. This clade is supported by dental and cranial features. See Wesley Hunt and Flynn 2005. Phylogenetic reconstruction is a critical first step in a comprehensive study of the evolution of Carnivora, or any group. Reconstructions of ancestral character states have greater associated errors as one proceeds from the tips to the root of a presumed ultrametric phylogeny, even in exceptional cases where the phylogeny is completely imperfectly known. It is in this context that fossil taxa provide two important sources of information for ancestral character reconstruction. First, fossil data provide a more complete sampling of the entire distribution of character states through the evolutionary history of a clade, documenting morphologies that, through extinctions, are no longer represented in the extant sample. Second, fossils provide temporal information associated with the specimens, which can be used to weight character state observations in the reconstructions. Recent morphological, molecular, and combined primary character analyses yield a well-resolved and stable higher-level phylogeny of Carnivora and parts of Carnivoromorpha. Morphological analysis indicate that Creodonta are the nearest relatives of Carnivoromorpha, while molecular results suggest that Pholidota are the nearest living relatives of Carnivora. There is strong support for monophyletic Carnivoromorpha, Carnivora, Caniformia, Feliformia, Arctoides, Pinnipedia, Musteloides, Pheloides, Herpestoides, and all traditional modern families. Early Cenozoic Carnivoromorphans, a monophyletic Viverividae plus a paraphyletic series of stem myacids, form basal outgroups to crown Carnivora. Based on those results, Flynn et al. 2010 named and provided a phylogenetic definition and diagnosis for the clade, including all Carnivoromorphans, except Viverividae, the Carnivora formes. Fossils placed within a robust phylogeny are crucial to interpretations of many evolutionary transformations. I hope that lecture was enlightening. I'll see you again in the preceding lecture where we actually do some coding.